Hi, my name is Jennifer Hong, and today I will be discussing Lab 3, Magnetic Field of a Bar Magnet. In this experiment, we will measure the distance dependence of the magnetic field due to a small bar magnet using the experimental and computational methods. The fundamental physics principles that we will be discussing are superposition of the magnetic field of the Earth and the bar magnet, on and off-axis magnetic fields, distance dependence of the magnetic field, and magnetic field due to a permanent dipole with Biot-Savart law. The first task that we will do is to compensate for the north, so you will download the magnetometer app and you will place the phone on the flat surface and turn it until the magnetic field in the x direction is 0. The next step is to find the magnetometer chip. So you will do this in the x and in the y direction of the phone. So you will first place the phone vertically on the ruler and place the magnet at the end, and you will slide the phone up and down until the absolute value of the x magnetic field is largest, and then you will turn it perpendicularly like shown in this picture and slide the phone up and down the ruler again until the absolute value in the y direction is largest. And then you will mark it with tape so that you can see the exact location of the magnetometer chip. After that, you will find the distance dependence of the magnetic field, and this will be done by using the location of the marked magnetometer chip as shown with the pink X, and you will slide the phone along a ruler with a piece of tape, taping down the magnet at the end until you reach certain values in the X and in the Y direction. You will then record the distance at which you received those measurements. After that, you will find off-axis magnetic field, and you will do this by taking a D perpendicular of a certain value and putting the phone exactly a 45-degree angle away from the magnet and recording the magnetic field at that point. So these are the observations from the lab. As you can see, for the off-axis measurements, D was 0.2597 meters, and the net magnetic field was 59.35 e to the negative 6t. In this graph, ln of bx versus ln of r, we found the line of best fit, and y was equal to negative 3.05x minus 0.7553. This equation will be used in the calculations. For the experimental observation, it was noticed that the magnetometer moves closer to the magnetic field increases in the x direction. For the calculations, we use the equation found in the observation, that was the line of best fit, and we found the distance dependence to be negative 3.05 and the magnitude of the magnetic moment to be 1,174,674 A meters squared. For the coding portion, we first inputted the physics constants and then created the magnet at the origin. After that, we created a function to measure the magnetic field, and we visualize the magnetic field using on and off axis arrows, and as well as a 45-degree angle arrow. And these are shown over here, as you can see with the arrow function. This is the computer model created through the code, and the white cylinder represents the magnet, the orange arrows represent magnetic field on axis, the blue arrows represent magnetic field perpendicular to the axis, and the pink arrow represents off-axis magnetic field at 45 degrees. So to compare the experimental and the computed value at 45 degrees, they are really similar in the values, except the z direction did not exist in the computed value. If we had not oriented the phone to compensate for magnetic north, the magnetic field of the Earth would have affected the results of the magnetic field of the bar magnet, making the results less accurate. Lastly, if we were to stick two identical magnets together end to end and run the experiment again, the magnetic field would increase, but the direction would be the same. And that concludes my lab. Thank you so much.